Welcome to the Explainer. If you're the kind of person who just loves taking the messy, moving world around us and breaking it down into clean, logical pieces, well, you are in exactly the right place. Today, we're going to tackle a fantastic physics problem. Now, I know the words physics or math can sometimes sound a little intimidating, but honestly, think of today's topic not as some dry textbook calculation, but as a really elegant, incredibly satisfying mystery that we get to solve together. We're going to watch a skier make their way down a snowy slope, hit a flat surface and coast to a halt, and we're going to translate that entire physical journey into a beautiful mathematical truth.
Okay, let's dive right into this. When you're skiing or really moving across any surface on Earth, there's this invisible force constantly interacting with you, just pulling energy right out of your movement. That force is friction. But friction isn't just some vague, generic concept, right? It's a measurable reality that depends on the specific interaction between two surfaces. For us today, it's the skis and the snow. So the central question we're answering in this explainer is, how do we actually calculate that invisible force? Specifically, how do we find what physicists call the coefficient of friction, using just a few basic measurements from a skier's path?
Here is our roadmap for today. We'll start with the skier's frictional puzzle, map out our variables, break down the forces, bring in the work-energy theorem, and finally, simplify and solve the whole thing.
Let's start with part 1, the skier's frictional puzzle.
So here's the exact setup we're working with from our source material. It goes like this. A skier of mass m skis 100 meters down an incline, making an angle theta with the horizontal. On reaching the bottom of the incline, she then coasts along the level ground for 50 meters before she comes to a stop. Calculate the coefficient of friction between the skis and the snow for theta equals 30 degrees. It's a really tangible story. Just imagine being that skier. You start at the very top of a hill, you glide down a 100-meter slope tilted at 30 degrees, you hit the flat ground, and you coast for 50 meters until friction ultimately brings you to a complete standstill.
Now, what's really interesting about this slide is how the free body diagram literally draws out all those invisible forces for us. You've got gravity, labeled Fg, always pulling straight down toward the center of the Earth. But because the skier is on a slant, the ground pushes back at an angle. That's our normal force, labeled N1. And pointing directly opposite to the skier's downward velocity, that's the force of friction, labeled FFR. This diagram is essentially our foundational map for understanding exactly what's happening to our skier at every single moment of their descent.
Moving on to Section 2, mapping out the variables.
Let's unpack our toolkit before we do any heavy lifting. What do we know? Well, distance 1, the slope, is 100 meters. Our angle, theta, is 30 degrees. Distance 2, that flat coasting section, is 50 meters. We're also given the mass of the skier, which is simply represented by the letter m. Now keep a close eye on that mass variable. It's kind of acting like a clue right now, but spoiler alert, it's going to pull a magic trick and completely disappear later on. And finally, our unknown, the treasure we're hunting for today, is the coefficient of sliding friction, written as the Greek letter mu with a subscript s.
All right, part 3, breaking down the forces.
We really need to split this trip into two distinct parts, Phase 1 on the slope and Phase 2 on the flat ground. The big, crucial conceptual difference here comes down to the normal force, basically how hard the snow is pushing up against the skis. On the slanted slope in Phase 1, the snow only pushes back perpendicularly to the angle of the hill. It is not supporting the skier's full weight directly against gravity. But in Phase 2, once they hit flat ground, everything changes. The surface is completely flat, meaning it pushes straight up, taking on the entire weight of the skier.
And this brilliantly illustrates why that distinction is absolutely crucial. On the left, for Phase 1, our normal force N1 equals mass times gravity times the cosine of the angle. Because friction relies directly on that normal force, the work done by friction here is negative mu sub s times that normal force times our first distance, d1. But look over on the right for Phase 2. On flat ground, the normal force N2 is just mass times gravity, mg, no angles to worry about. So the work done by friction there is simply negative mu sub s times mg times our second distance, d2. Two completely different phases, two totally different equations for friction.
Which brings us to Section 4, the work-energy theorem.
So, the crucial point here is grasping what this work-energy theorem actually does for us. In plain English, it tells us that the total change in an object's energy, from the very start of its journey to the absolute end, is exactly equal to the work done against non-conservative forces, like friction. Simply put, all that awesome potential energy our skier has at the top of the mountain, it is completely eaten up by the friction of the snow by the time they come to a dead stop.
Let's look at how elegant this is.
In our initial state, at the very top of the hill, the skier is resting before the plunge. So, kinetic energy, 0. All their energy is stored up as potential energy, driven by how high up they are. And based on our geometry, that height is d1 times the sine of theta. So total initial energy is purely potential, m times g times d1 sine theta. Now, fast forward to the final state. The skier has coasted to a complete stop on flat ground. 0 height left, 0 speed left. So the final energy is a big, fat, perfect 0.
Now we build our master equation. Final energy minus initial energy equals the work done by friction. 0 minus mg d1 sine theta equals, well, it equals all that friction from phase 1 and phase 2 combined. To tidy up the math, we just multiply the whole thing by -1, so we're working with positive terms. That gives us our starting potential energy perfectly balanced against the combined friction from the slope and the flat ground. It's literally just balancing the scales of the universe.
Finally, part 5, simplifying and solving.
Let's move to step 1 and see how this builds, because this is where that magic trick I promised earlier happens. We set our total energy loss equal to our total friction work, like we just saw. Now look closely at step 2. Every single term on the left and right side has an m and a g, mass and gravity. Because mass and gravity affect the pull down the hill and the friction pushing back equally, we can just divide both sides by mg. Boom, canceled out entirely. This whole complex problem suddenly doesn't even care how heavy the skier is. Then step 3, we simply factor out our single unknown, mu sub s, to isolate it.
Just take a second to appreciate the beauty of this isolated formula before we throw real numbers into it. Once we factor out mu sub s on the right side and divide to isolate our unknown, we get this beautifully clean mathematical truth. Mu sub s equals our downward distance divided by our combined friction variables. It is such a perfect, neat distillation of the physical world right there on the screen.
All right, grand finale time. Let's take those knowns from our toolkit and plug them into our shiny new equation. We know our slope distance, d1, is 100. Our angle theta is 30 degrees, and the sine of 30 is exactly 0.5. The cosine of 30 is roughly 0.866, and our flat coasting distance, d2, is 50. So up top, the numerator is 100 times 0.5, which is 50. Down below, the denominator is 100 times 0.866, which is 86.6, plus the 50, giving us 136.6. We divide 50 by 136.6, and we get approximately 0.366. Following standard scientific practice, we round this to 2 significant figures, delivering our final payload, a coefficient of friction of exactly 0.36. We did it! We tracked the invisible forces acting on our skier, we mapped the variables, applied the work-energy theorem, wiped out the messy algebra, and found that the friction coefficient between those skis and that specific snow is, for sure, 0.36.
But before we wrap up this explainer, I want to leave you with a provocative thought rooted right in that magic trick we pulled earlier. If a tiny kid went down this exact same slope or an adult wearing a massive heavy backpack used the exact same skis, would this final coefficient of friction change at all? Because mass canceled out entirely, think about what that universal truth means for how engineers design everything from roller coasters to the tires on your car. Thanks for joining me today. Keep looking for the hidden math in the world around you, and I will catch you in the next explainer.